2012, Zlatan Ibrahimovic scored this amazing bicycle kick for Sweden against England.
Hart didn't quite get that right. Oh, look at that! That is absolutely astonishing!
For my project, I'm going to do a video analysis of this bicycle kick. We have to make some assumptions. First, the rotational acceleration of the player's leg from rest until contact with the ball is constant. This is likely true as muscular force during a kick is usually also constant, driving a constant acceleration. Second, the radius of circular motion is taken as the distance between the hip and the front of the player's ankle. This is also likely true as seen in a slow motion close-up analysis of the kick. Thus, the foot is neglected in the calculation of the length of the radius. We already know that the player is 195 centimeters tall. We can use this to put a proportional scale next to him to find the length of his leg as approximately 100 centimeters tall. This is our radius. Using a stopwatch, we see that his foot rotates 140 degrees in just 0.57 seconds. To properly analyze the projectile motion of the ball, we need to reframe the shot into a two-dimensional frame. Keep in mind that for this trajectory, the drag force on the ball has been neglected as the ball was rotating after the kick, and the ball experiences less drag because of the Magnus effect, which is a lifting force that occurs when a rotating body moves through a fluid. The motion of the kick started with Zlatan's leg at rest. Thus, the initial rotational velocity, or omega 0, is 0. We can use the formula alpha is equal to delta omega by delta t to find the rotational acceleration brought about in the player's leg, which is 15.05 radians per second square. We can also find the moment of inertia on the leg using this formula. The mass of Zlatan's leg is an approximate percentage of his known weight. This gives us the moment of inertia as 5.67 kilogram meters squared. Using the acceleration we found, we can also find the final rotational velocity. We get this as 8.57 radians per second. This is for the rotation of the player's leg from rest until contact with the ball. To get torque, we multiply inertia and acceleration to get 85.45 Newton meters of torque. We can use this to find the force applied on the ball by dividing torque by the radius. This gives us 85.45 newtons of force on the ball. The impulse on the ball is force into delta time. We can take delta time as 0.1 seconds, which is the time of contact between the ball and the foot. This is not a negligible value since the ball has some elasticity allowing it to be in contact for a measurable time. Our impulse force is thus 8.545 Newton seconds. Now we use this impulse force to find the initial velocity given to the ball. We know that the regulation mass of a ball is 0.43 kilograms. Using velocity is equal to impulse over mass, we get the initial velocity as 19.88 meters per second. Using this derived equation for range, we can also relate the range to find the angle made between the initial velocity and the horizontal. The range is known to be 29.53 meters. By relating this, we get our angle of theta as 24.3 degrees. Now that we found a lot about what we need to quantify the bicycle kick and the projectile motion of the ball, let's use this to admire the precision necessary to score this goal. As we see in the video, the defender was only a meter away from intercepting the ball. The ball was also only a meter below the crossbar of the goal. Using this, we can estimate that if the range was a meter less or a meter more, the player wouldn't have scored the goal. Using range is equal to u squared sine 2 theta over g, we can find that the angle theta has a range of 22.5 to 24.6 degrees to stay within the necessary range to score the goal. We must admire the fact that with no time to think, Zlatan Ibrahimovic executed this extremely precise kick perfectly, making it fully deserving of winning the Puskás Award for best goal that year.